So when x is greater than or equal to minus 4 by 3, so if we have h of x is equal to g of f of x, right? So when x is greater than or equal to minus 4 by 3, g of f of x is defined. Now we know that the domain of g is x is greater than or equal to 3. So when x is larger than or equal to minus 4 by 3, f of x will be greater than or equal to 3. Meaning when we input this f of x into our function g, we're satisfying our domain. We're satisfying this restriction basically, right? So when we're inputting our value of x, which happens to be greater than or equal to minus 4 by 3 into our function f, we get an output f of x which is greater than or equal to 3, which allows h of x to be defined. Right, so let's consider a different problem. Let's say we have h of x is equal to f of g of x in general, right? Meaning we can write this also as h is equal to f of g. Now suppose h of x is defined for all values of x that is in the domain of g. Now is the range of g part of the domain of f? Right, so now we have a function h of x which is just the composition of two other functions f and g. Now we're told that h of x is defined for all values of x that is in the domain of g. Now is the range of g part of the domain of f? Right, so we have h of x is equal to f of g of x, right? So when we consider a value of x, that is in the domain of g, then if we consider that value of x as an input into the function g, we get some corresponding output g of x, right? And we know that these outputs make up the range of g, right? So the range of g is just a possible set. It's just a set of all possible outputs, right? So g of x is an output and it forms the range of the function g, right? And then this g of x, this output, becomes an input into our function f, right? We're considering g of x to be an input of our function f, right? So in order for h of x to be defined, and we're told that h of x is defined for all values of x that is in the domain of g, right? So in order for h of x to be defined, f of g of x has to be defined, meaning g of x needs to be defined, and g of x needs to be in the domain of f, right? G of x needs to be in the domain of f, otherwise our function f itself will not be defined, right? And since we know that g of x is just a range of our function g, and we know that g of x is now in the domain of f, in order for h of x to be defined, then the range of our function g, the range of g is going to be in the domain of f, meaning the range of our function g is definitely a part of the domain of f, right? Now must the domain of H be the same as the domain of G. Right, so this is our question. Must the domain of H be the same as the domain of G? Once again, we're still considering H is equal to f of G. So H of x is just equal to f of G of x, right? Right, so we're still considering that H of x is defined for all values of x that is in the domain of G, right? We're still considering this. Now we just want to know if the domain of H and the domain of G are the same, right? Now, if x is in the domain of G, then G of x is defined, right? If x is in the domain of G, then obviously G of x is defined, right? And we know that G of x is just the range of G, and the range of G is in the domain of F. This is in the domain of F, right? And if it is in the domain of F, then f of G of x is defined, and thus H of x is defined, right? So in this case, if for some value of x, we have G of x is defined, then this x that is in the domain of G of x has to also be in the domain of H, right? If x is in the domain of G of x, then G of x is in the domain of our function f, and thus H of x can be defined. Meaning, for every value of x that is in the domain of our function G of x, this value of x is also in the domain of our function h. Meaning, the domain of h and the domain of G are the exact same. Right, so now let's consider a different problem. Let's say we have f of a, which is equal to, okay, this. We have f of a, and this is equal to a minus 2, right? So we have a function f of a, and we have another function f of a comma b. So now we have two inputs, and we've worked with two inputs before, and this is equal to b squared plus a. Right, and now we want to find the value of f of 3 comma f of 4. Right, we want to find the value of this. Right, so in this case, we see that a is equal to 3 and b is just equal to f of 4. And we can easily find the value of f of 4, right? So we can consider f of 4, and this is equal to, well, we just substitute 4 into this function. So we have 4 minus 2, we get 2. Right, so f of 4 is equal to 2. So we have f of 3 comma f of 4. This is equal to f of 3 comma 2. Right, and we substitute these values into this equation, into this function, and we get 2 squared plus 3. Right, so we have 4 plus 3, we just have 7. Right, so f of 3 comma f of 4 is just equal to 7. Right, so let's consider a different function now. We have f of x. This is equal to 3x minus 1. Right, and now we want to find f of x and f of f of x. Right, so now these two things might seem especially this. It might seem a bit disgusting and very complicated, but it really isn't. It's a fairly simple process, right? We're just feeding the output of a function into the function itself in this case, and we're doing the same thing for this case, but twice, 2 more times. So we have f of x, right? So we're just substituting 3x minus 1 into the function again. So we have f of 3x minus 1, right? This expression is our input. So we substitute it into our function. So we have 3 times 3x minus 1 minus 1, right? And this just gives us 9x minus 3 minus 1, which is 9x minus 4, right? So f of x is just equal to 9x minus 4. Right, so now we found this. But the next part is actually pretty easy. We've already found f of x, right? Which is 9x minus 4. All that we have to do is just substitute this expression, 9x minus 4, into our f of x in this whole composition. Right, so now if we have f of x, then this is equal to f of 9x minus 4. Right, so we just substitute 9x minus 4 into our original function. So we have 3 times 9x minus 4 minus 1. Right, and this gives us 27x minus 12 minus 1, which is 27x minus 13. Right, so f of x is just equal to 27x minus 13. Right, so now suppose that we have some function g. Suppose we have some function g of x, and this is equal to ax plus b, where a and b are just some constants. Right, now we just have to find all possible pairs a comma b such that we have g of x is equal to 9x plus 28. Right, so we just have to find the values of a and b for which g of x is equal to 9x plus 28. The very first thing we can just do is find the composition algebraically. We have g of x, and this is equal to a times ax plus b plus b. Right, so we just substituted the function g of x into the function itself again, and this gives us a squared x plus ab plus b. Right, and we know the value of we know what g of x is equal to. Right, it should be equal to 9x plus 28. So we have a squared x plus ab times ab plus b is equal to 9x plus 28. Right, so we have a squared x plus ab plus b is equal to 9x plus 28. And now we see that on the left side and on the right side we both have an x term. We both have a term that contains the variable x. Right, so now we can just equate the coefficients of this variable. Right, so we can just equate the terms together. So we have a squared x is equal to 9x, and now we can just divide both sides by x, and we have a squared is equal to 9. All we did was just equate the coefficients of x together. Right, and from this we can just take the square root on both sides to find the values of a. So a is equal to plus or minus square root of 9 is equal to plus or minus 3. So now we have two values of a. We have a is equal to 3 or a is equal to minus 3. Right, and now we can just easily find the corresponding values of b when a is one of these values. So We can also see that AB plus B is also a constant on the left side, and on the right side we have 28 as a constant. So we can just equate these two sides as well. So we have AB plus B is equal to 28. Right. So now when A is equal to 3, when A is equal to 3, we have 3B plus B is equal to 28, and this is 4B equals to 28. We divide both sides by 4, and so this gives us B is equal to 7. Right, so when A is equal to 3, B is equal to 7. So now we have found one ordered pair in this form. So A comma B is equal to this. Now when A is equal to minus 3, once again, we can use this equation. We have minus 3B plus B is equal to 28. And now we have minus 2B is equal to 28. So B is equal to 14, or B is equal to minus 14, since we're dividing by minus 2. So once again, when A is equal to minus 3, B is equal to minus 14. Right? And we can check our values of A and B by just substituting these A and B values back into our g of x, which is equal to a squared x plus ab plus b. Right, so we have g of x is equal to a squared x plus ab plus b. And if we were considering this pair, if we're considering the pair 3, 7, so now we have 3 squared x plus 3 times 7 plus 7. And this gives us 9x plus 21 plus 7, which is just equal to 9x plus 28. Right, so we have obtained 9x plus 28, which was given in the question before. And we can do the same thing for this pair, and you can try this yourself. Now, when we're inputting the output of a function back into that function itself, so let's say if I have a function g, and for some value of x, I get an output g of x, and I feed this output back into the same function itself. Right, that would give me g of x. Right. Now, another way of writing this is with the 2 in the superscript of x. Right. We can write this as this. Similarly, if I feed the output of a function back into that function itself 5 times, so if I have g of g of g of g of g of x, then I can also just easily write this as g with a superscript as 5 of x. Right. And if I do it for n times, if I feed a function or the output of a function back into the function itself n times, then I can denote that as this. So this is the special notation that we can use, because writing it out fully can take a bit of time and it can get pretty confusing. Right, so now let's take a look at a function f of x is equal to square root of x and g of x, which is equal to x squared. Now, if I find two compositions of these two functions, if I find f of g of x and g of f of x, now I want to know, are these two compositions the same? Are f of g of x and g of f of x the same? Right? Now, how do we find out if these two things are the same? So what is f of g of x? F of g of x is just the square root of x squared, right? And g of f of x is just the square root of x whole squared. Right. Now we can find the domain of g from this given function of g. So the domain of g, we can see that it can be the set of all real numbers, right? For the domain of G, we can see that X is an element of the set of all real numbers. We can have any number from the set of real numbers. We can have a negative number or a positive number. But we can see that the range of G is always going to be non-negative, right? Since we have a squared term over here, that means that G of X will always be non-negative, right? So G of X is an element of the set of the interval from 0 to positive infinity. Right, so we can see from this that because the domain of G is a set of all real numbers, that means that f of G of X is defined. Oh, we have an extra. We can see that f of G of X is defined for all real numbers. Right, because we can see that we have an x squared, right? So we can take any value of x, and because of the squared term, we will get something non-negative. And under the square root, f of G of X can then be defined, right? So the domain of f of G of X, so the domain of this is X belongs to the set of all real numbers, right? But however, if we take a look at G of f of X, right, we can see that G of f of X is equal to the square root of X squared, right? So now there is clearly a restriction on the function of f. So the domain of f is that x is greater than or equal to 0, right? So x is an element of the interval 0 to positive infinity, right? And because of this, our values of x in our function f has to be non-negative, right? So the domain of G of f of x is always going to be non-negative, right? So G of f of x is an element of the interval from 0 to positive infinity. Right, so all non-negative numbers are in the domain of G of f of x, right? Because if we did not consider this restriction, then f of x would not be defined, and thus G of f of x would not be defined. So our domain of G of f of x has to be non-negative. That means since G of f of x and f of G of x have different domains, therefore these two compositions are not the same. Right, so these two compositions or these two functions are not the same.